This video is about significant figures. Some of you have at least heard of significant figures. A few of you understand them in some general terms. So hopefully we'll clarify what they are and what their purpose is in this video. At first, they will seem a little bit confusing. Okay, I can promise you at some point in this video you will be confused. But as you start to use significant figures and apply them in each of your calculations, they'll start to make a lot more sense. And it's kind of one of those things that if you apply a good probably hour and a half or so of practice, you will be set. Okay, sometimes it'll even take less than that. But I don't think it'll take more than about an hour and a half to really catch on to what significant figures are and why you have them. First of all, a definition here. Significant figures in a measurement include all of the digits that are known, plus one more digit that is estimated. Okay, so what significance really have to do with is they have to do with the precision of the instruments that you're using. Now remember, in the previous video you saw these scales, or I guess we call them balances is the correct term. And a balance kind of looks like this as I draw it really poorly. Sort of looks like this, and then it has a screen here. And on that screen, it probably comes out here. Okay, this is really a bad drawing. But on that screen, it's got something that will be like 0.132. Okay, so when you measure the mass of something, and if it says 0.132 grams, okay, then when you communicate that number to somebody else, you have to inform them that this measurement was only accurate up to the 1,000th place. This is the 1,000th place, okay? So you've got 0.132 grams, okay? Now you do not want to give them the impression that you knew that this was actually 0.132000, okay? Because this scale says nothing about the digits in the 10,000th, 100,000th, or millionth place, okay? So for you to assume that those were zeros in those places is a wrong assumption, okay? Because we really don't know. If we had a more precise scale, we may have figured out that this was actually a 7, or that this was actually a 5, and this was actually a 1, okay? We just don't know what these are. So therefore, we cannot report digits beyond 0.132. Anything beyond that would be insignificant, okay? Significant means that they are known digits, okay? So let's go and we'll give an example that will tell us a little bit about how the measuring device you use dictates the precision that you can apply in your problem. All right, so here we have, in this example, we have 3 different meter sticks, okay? Now these are a little bit weird because you wouldn't really see a meter stick like this, but they give you a good idea of why you can only be confident to a certain number of decimal places based on the measuring device you're using, okay? Now the first measuring device is a really weird one, okay? You essentially know where 0 is down here and where 1 meter is, okay? But you don't know anything in between because you don't have the little tick marks that you'd be used to in between that count off exactly how long something is, okay? So with this one, it's really kind of simple, okay? All you can do is you can estimate the ones place, because in the ones place you know it's between 0 and 1, okay? And if it's between 0 and 1, then in the ones place you must have a 0, okay? In the tenths place, okay, we have to estimate because we don't have tick marks. If we had tick marks, then we would know exactly how long that board is in the tenths place. But in this case, it's just an estimate, okay? And you look at the length of this board, and we can estimate. We look about how far it is. We say, here is 0, here is 1. It must be about, maybe 60% along the way. Okay, so I'm going to put a 0.6 here. That number now is estimated, okay? This number is estimated. And if you remember right on our definition here, it said that we can have one more digit that is estimated, okay? So 0.6 is appropriate. Now, would it be appropriate to say, oh, it's 0.61032? Of course not, because we just estimated that 0.6, that tenths place. There's no way we can estimate the next hundredths place, let alone 1,000th, 10,000th, or millionth, or 100,000th. So we have to get rid of these. We can only estimate up to the tenths place in this answer. And that's how precise our instrument permits. Okay, in this next one, we have more precision in this ruler because now we've marked off the tenths places. We've got 10 centimeters, 20 centimeters, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, so our tenths are all marked off. So now we have some extra confidence in this case. Okay, we still know that in the ones place it must be a 0 because obviously it's between 0 and 1, okay, meters. Let's make sure we put meters up here so we're really clear. Try that again. For some reason it does that sometimes. Put a meters right there. So it's the first decimal, or the first, not decimal, but the first in the ones place, it's got to be a 0 because it's somewhere between 0 and 1. So we know that is going to be a 0, okay? Now we get to the tenths place, and now we know it's between 6 tenths and 7 tenths, okay? So we know if it's between a 6 tenths and 7 tenths, then the digit that will go in the tenths place is a 6. Now we can be confident of that. Up here we had to estimate that, but now we can be confident because we see the markings here that's between the 6 and the 7 tenths, okay? The next one is estimated, okay? We don't, if we had little tiny tick marks like this, okay, we could know for sure which number should go in the hundredths place, but we don't have tick marks, okay? So now we have to estimate the hundredths place, okay? And so if we do an estimate here, we can estimate it at, say, where is that? Okay, so here is this would be a 0, and this would be a 10 in the hundredths place, and it's about maybe a 10% of the way between those marks, so we're going to put a 1. Okay, and this one is estimated. That means we can't do any more. That's got to be all we can, that's all the significant figures we can determine based on this meter stick. Finally, this next meter stick is much more precise. We have now added the hundredths in there, okay? So this one only had the tenths. Now this one has the hundredths. You can see these little lines for the hundredths. Okay, so now let's go through this again. Of course, we know our first number is 0 point, and then our next number is going to be between 6 and 7, so it is a 6. Okay, and then the next number is going to be somewhere between 1 and 2. Okay, so it's like 61, I'm sorry, let me correct that. It's going to be somewhere between 0 and 1. Okay, so we can put that the next number, because it's between a 0, like 6, 0 and 6, 1, that means the next number must be a 0, okay? Because obviously if something's going to be between 0 and 1, it must have a 0 there. Okay, then we get to estimate one more. Okay, now look where this line goes for the end of the board. It looks like it is most of the way. If we look at where the 0 mark is and the 1 mark, then this is probably 2/3 of the way through. So we can put it, our estimated number might be a 7. Now who knows, you might have put a 6 there. Doesn't really matter, okay, because it's an estimated number. So it's fine if you put a 6, but we know for sure that we cannot come up with any more significant digits. Okay, so based on, again, the number of significant figures is based on how precise your instruments are. This instrument right here could only give us precision up to the tenths place. This one gave it up to the hundredths place. This one to the thousandth place. Now we know why we have significant figures. Again, it's based on the precision of the instruments we're using. The next section, we're going to talk about how you communicate to other scientists the number of significant figures that you have in your measurements. Okay? Not only how you communicate it, but also how you interpret it when another scientist writes down a measurement. Okay? So there are some basic rules here, and these are not mysteries of math or anything like that. These are just conventions. They're rules that somebody made up so that when scientists communicate, they know what each other is talking about. Okay? The first rule, number 1. Non-zeros always count as significant figures. Okay? So when we have a number that says 3, 4, 5, 6, okay, we know that that number has 4 significant figures because all of the digits in that number are non-zeros. So that has 4 significant figures. Okay, rule number 2. Leading zeros do not count as significant figures. Okay, so if there are any zeros before you get to a non-zero digit, then those zeros do not count. So these first 2 zeros are not significant. I'm going to cross them out, which just means they're not significant. Okay, so in this case, we have 3 significant figures. All right, now we'll get to why we're counting these momentarily, okay? But right now, we're just trying to see how many significant figures we have in each problem. Now, that's not saying this number is not 0.0486. We just know that only 3 of these digits are significant. This has 3 sig figs. Okay, again, we'll get to why we're counting these in a moment. Number 3, captive zeros. So captive zeros always count as significant figures. All right, so where is our captive zero? This is kind of like a video game, you know, we're trying to rescue the captive princess maybe. And there is a captive zero here because you have a non-zero digit followed by a 0 followed by a non-zero digit. This 0 is captive because it is surrounded by 2 sig figs. And so if it is a captive 0, then it counts as a significant figure. So this has 1, 2, 3, 4 significant figures. Trailing zeros are significant only if the number contains a written decimal point. Okay? Now that might seem a little bit random, but again, this is just the way that scientists communicate to each other. This is a convention that has been created so that when one scientist writes down a number, another scientist knows what that number means. So, trailing zeros are significant only if the number contains a written decimal point. So in this case, there is a decimal point in the number. That means every single one of these digits are significant. There are 4 significant figures. Okay, let me give you another example. We're going to go over some examples in a moment, but I'll give you one really quickly. Let's say you had the number 2300, okay? Now, in this number, there is no decimal point. Therefore, trailing zeros are not significant because trailing zeros are only significant if the number contains a written decimal point. Therefore, if it does not contain a written decimal point, then those trailing zeros are not significant. And in this case, this one is not significant, this one's not significant. You only have 2 significant figures. This would be 2 sig figs. All right, there are 2 special situations. These are kind of exceptions. And there's a good reason for them. You'll understand it. First of all, counted items, such as 23 people or 425 thumbtacks, they always have unlimited significant figures, okay? So let me help you understand this. Okay, if you're counting people, you get to 23 people, okay? People come in whole numbers, all right? They don't come in 7/10 or 2/3, okay, or 0.01. They come in whole numbers. So when you get to 23, you know that that's exactly 23 that you've counted. You've got 23.000 people. Okay, you can have as many zeros as you want because you know it's exactly 23. It's not like there's some concern that you weren't precise enough and maybe there was another 100th of a person there. Okay, same thing with counting anything. Anytime you do a count, you can assume that you have as many significant figures as you need. Okay, and we'll talk about why that's important in a moment. Another case when you have unlimited significant figures is when you have a defined value. For example, 60 minutes in an hour, okay? An hour is defined as 60 minutes. That means it's 60.000000000 minutes in an hour, okay? It's exactly 60 minutes. So that means you could have as many significant figures with 60 as you want. Okay, here's some practice. I'm going to do the first 2, and I'll have you work out the rest of them on the side and then give an answer, and then I'll work through them and show you how it works. Okay, the first one has 5 significant figures. Here's why. Okay, obviously these 2 digits we know are significant. These two zeros, they're captured, or they're captive. Now, the other one that can be tricky is this last one. It is a trailing zero. But because there is a decimal written into this problem, you know that all of these, that zero is significant, and you have a total of 5 sig figs here. Okay, now the next one, also relatively easy. You have a trailing zero. Trailing zeros only are significant when you have a decimal. You do have a decimal, therefore you have 4 sig figs. Okay, the next one, I want you to work this one out. Okay, go ahead and work this out on the side, and then come back once you're done. Okay, this one is a case where you have, obviously you have 1, 2, 3 non-zero digits, then you have 2 captive zeros, those are both significant, and then we have the question of this last one, all right? Trailing zeros are only significant if you have a decimal. You do not have a decimal here, therefore that is not significant. You only have 1, 2, 3, 4, 5. That is correct. All right, now this one is a little bit different, but actually you'll find easier. Okay, scientific notation is great because it makes very clear how many significant figures you have. All right, here's what I'm going to tell you. You can, when you're counting significant figures, you ignore this part. This is just for the sake of counting significant figures. You don't even look at the 10 to the third. That's only for the sake of placing your decimal. It has nothing to do with significant figures. All you look at is this number over here, okay? And that number is pretty easy. You've got 3.29, okay? And the exact same rules that we've talked about apply in figuring out the number of significant figures for that. Of course, that's going to be 3 significant figures. All right, you work out this next one, okay? Go ahead and work it out on the side and come back when you're done. Okay, this one, we have a case of leading zeros. This is the first one we have with leading zeros. 3 leading zeros, those are not significant. We only have 2 significant figures. And I think we have one more. Aha, we do. All right, look at this one. All of those digits, this must have a lot of significant figures. Okay, go ahead and figure this out on the side and then come back. Okay, let's look at how this came out. Hopefully you did well on it. In this case, it looks like a lot of significant figures. In reality, all of these are trailing zeros, okay? Trailing zeros are not significant. So we only have 2 significant figures. Only, I guess I should have put lines through these. Let's go like this to be consistent. Only these 2 are significant figures. 2 significant figures. All right, finally 5 dogs. Okay, we're not worried about possibly having 5.01 dogs or 5.0123 dogs, okay? We counted 5 dogs. We know we have exactly 5 dogs. Therefore, we have unlimited significant figures.
Now that we've talked about how the scientist communicates the number of significant figures in the measurements they communicate, we need to talk about how we use those significant figures in calculations. Okay, and this is the most important part. And there's 2 major rules. There's completely different rules for addition and completely different rules for subtraction. Okay, but the general principle is this. Okay, the calculated answer cannot be more precise than the least precise measurement from which it was calculated. Okay, we could give some examples around that, but just for the moment, just remember that your goal is to find whichever number in the problem is least precise and make sure that the answer is not more precise than that. Okay, and the concept is similar to what it mentions here. It's like the idea that a chain is only as strong as the weakest link. Okay, let's talk first about multiplication and division. This is what's important. There are going to be 2 different rules. There's going to be one rule for multiplication and division. There's going to be a totally different rule for addition and subtraction. Okay, so you need to keep these 2 rules separate because you apply them completely differently. First of all, multiplication and division. Here's what you do. You count the significant figures in each of the numbers in the problem. Your answer cannot have more significant figures than a number with the least significant figures. Okay, let me interpret that. Okay, so we have a problem here. we count our significant figures. In the first number, we have 3 significant figures. In the second number, we have 2 significant figures. So based on these instructions, our answer cannot have more significant figures than the number with the least significant figures. Okay, so our answer can only have 2 significant figures. All right, let me erase this. So here's what our calculator said. It said 12.76. But we know we could only have 2 significant figures. So we look at this and we say 1, 2. All right, so like we see here, our answer has 2 significant figures, but there's something weird. Why wasn't it 12? Here's the reason. You look at your first non-significant figure and you use that for rounding purposes. Okay, because this number is 5 or greater, then we're going to round this number up, so it becomes 13. If it was less than 5, we would have left it at 12. The important part here is that our answer only has 2 significant figures, and we count those from the left. Okay, so we had 2 significant figures, we say 1, 2, and then we use this first insignificant figure for rounding purposes. And here is just an overview of rounding, just like I barely mentioned. You look at your first non-significant figure for rounding purposes. If it is 5 or greater, you round the last significant figure up. If it is less than 5, leave it the way it is. All right. So as we just showed in this problem, we had 3 significant figures, 2 significant figures. Therefore, our answer can only have 2. So we say 1, 2 that are significant. We look at our first non-significant figure, and that means it is, as it mentions up here, 5 or greater. So that means we're going to round up. So our answer would be 13. Here's a few practices on multiplication. So what's going to happen here is it's going to show the calculation, and then it's going to show what the calculator says, and then it's going to show the answer. So I'm going to do the first 2, and then I'm going to ask you to do the next ones and give me the answer on the sidebar. All right. Okay, we have 3.24 meters times by 7.0 meters. Comes out to be 22.68 meters squared. Right, so the question is, what should our answer be? This part is easy, of course, getting to here. All we do is we count. We say, okay, we've got 3 sig figs here, 2 here. The number with the least significant figures is 2. Therefore, our answer can only have 2 significant figures. So we have 1 significant figure, 2 significant figures, and then 1 non-significant figure that we look at for rounding purposes. This 6 is greater than 5. It is 5 or greater. Therefore, we're going to round the answer up, and we get an answer of 23 meters squared. All right, next one. Okay, we've got 100.0 grams divided by 23.7 centimeters cubed. Okay, so let's see what our answer is. Obviously, we're doing a density calculation here. So here's what our calculator says. It has all of these numbers. Okay, if we were to report it like that, we would make other scientists think that we had extremely precise instruments that measured to the, billionth of a gram, okay? But that is extremely rare to have measurements that precise. In fact, you will never find that in a high school lab. So we need to report this correctly. Let's look at our 2 numbers in our problem. One has 4 significant figures, one has 3 significant figures. The one with the least significant figures has 3 significant figures. So we start counting from the left. 1, 2, 3. Okay. Then we look at our first non-significant figure. If it is 5 or greater, then we round the last significant figure up. So in this case, we'll be rounding up to get an answer of 4.22 grams per cubic centimeter. See, these aren't too bad. Let me give you one. You work on this one. All right, this is a nice one. It's a little bit tricky, but not too bad. So go ahead on the sidebar. I'm going to even give you the calculator number, but go ahead and figure out what the answer is and come back and report on it. Okay, welcome back. Excuse me. Let's look at our two numbers in our problem. This one, okay, now these are leading zeros. They do not count as significant figures. We only have one significant figure in this problem, or in this number. Now this one, on the other hand, has 1, 2, 3, 4 significant figures. This one has 4 significant figures. Okay, but remember, a chain is only as strong as its weakest link. The weakest link in this problem is the first one with one significant figure. Therefore, when we do this calculation, we can only have an answer with one significant figure. That's kind of weird, I know. You think, why do we only have one significant figure? That's the way it is, because this is the weakest link. So we go down to our answer here, and we say, okay, we start from the left to the first non-digit zero, or non-zero digit, and that is our last significant figure. Then we look at our first non-significant figure. It happens to be 5 or greater, therefore we need to round up. So we only have one significant figure, we're going to round up, and our answer is going to be 0.05 centimeters squared. All right, go ahead and work this one out again on the sidebar and see if you can figure out. This is division, which follows the exact same rule as multiplication. All right, welcome back. This one, again, we count the significant figures. We have 3 here. Sorry about that. See, I messed up. It's a good thing you caught me. All right, we only have 2 significant figures, because remember, trailing zeros are only significant if there is a decimal place. So this one has 2 significant figures. This one also has 2 significant figures. This one has a trailing 0, but it also has a decimal point. Therefore, that trailing 0 counts as a significant figure. Each of them have 2 significant figures. So our answer must have 2 significant figures. We count starting from the left, 1, 2, then we look at our first non-significant figure. It's 5 or greater. Therefore, we're going to round up the last significant figure, and our answer is going to be 240 meters per second. And one note on this answer over here, you notice that there is not a decimal. If there would have been a decimal, we would have been indicating that that last 0 was significant. It is not significant. We don't put in a decimal. All right, try one more problem on the side, and then we'll go on to the last one. So here's our answer. Try this problem and come back in a second. Okay, let's look at this one. This one's actually not too bad. We have 1, 2, 3, 4, 5 significant figures here, and then 1, 2, 3 significant figures here. The least significant figures is 3, therefore our answer can only have 3. We go 1, 2, 3, and then this is our first non-significant figure. This is the first time that is less than 5. If it's less than 5, we leave the significant figures as they are, and our answer would be 5,870 pound-feet. All right, the last one, I'll just work through this one with you. We have 1, 2, 3, 4 significant figures. Remember, we have a trailing 0, but we do have a decimal, therefore that is significant. And then we have 3 significant figures here, and therefore our answer must only have 3 significant figures. We count from the left, 1, 2, 3. First non-significant figure is 5 or greater, therefore we're going to round up. We're going to round up this last significant figure, and our answer becomes I'll just push the button here, 2.96 grams per milliliter. All right, next principle, addition and subtraction. This is I'm going to write it up here just so you know, completely different rule. It is like you have to throw out everything you knew about multiplication and now learn a different rule for addition and subtraction. So make sure that you see that change and you apply these rules differently. the number of the decimal places in the result equals the number of decimal places in the least precise measurement. So that definitely sounds a little bit confusing. Let me clarify that, okay? If we have two numbers that we're adding together, we're going to do a number here, 623.5 and 1.25. All right, we have two different numbers here. Now what we're looking at is how many decimal places each of these numbers have. Again, we're not counting significant figures, all right? What we're looking at is which of these numbers has the least decimal places. Okay, so this first one has one decimal place. It's got a digit in the tenths spot. The second one has two decimal places. It has digits in the tenths and the hundredths. So our number with the least decimal places is this number, 623.5. So that means that our answer can only have digits up to the first decimal place. Let me give an example here to clarify that. Here's how I like to look at this. I always like to add these up vertically. Okay, so I like to put 1.25 plus 623.5. All right, here's what I like to do. I like to look at my number with the least decimal places, which is this one, and then I like to draw a line down to the right side of that decimal place. Okay, this tells me that my answer can only have digits up to the tenths place. Okay, so what I do is I add all of these together. I get 5, 7, 4, 2, 6. So 624.7 and then a 5 here. Now, because this 5 sits to the right-hand side of my line that I drew, I know that this 5 is not significant. So I'm going to put my little arrow on it because I'm going to use that for rounding purposes. And I know that 1, 2, 3, 4, these are my significant digits. So I'm going to use the 5 and I'm going to round up. So here's my answer. It's going to be 624.8. All right, and we didn't put units on that, but we should have units. But the key here is this. You look at the number with the least decimal places, and your answer can only have digits up to that decimal place. I cannot have hundredths if the least decimal place is tenths. I cannot have thousandths if the least decimal places in my problem is hundredths. Let's do some practices. Oh, here's one practice. Let's do this one. All right, 6.8 plus 11.934. Which of these two numbers has the least decimal places? Of course, that's going to be 6.8 because it only has one decimal. Okay, this one has 3 decimals. This one only has digits up to the tenths place. Therefore, our answer can only have digits up to the tenths place. Again, I like to do this vertically. It just makes a lot more sense to me. 934 plus 6.8, and then because this 8 is this second number, 6.8, has the least decimal places, our answer cannot go past the tenths place. Let's put a line there. Okay, we're going to get 3, 4, 9 plus 8 is 7, and then of course 8 and 1. Okay, so we will have a decimal here, and then we look at our first non-significant figure, and because it is less than 5, then we keep the significant figures as they are, and our answer becomes 18.7. All right, hopefully that makes sense. Let's go on to some problems. I'm going to do the first two. I'll ask you to do the next ones, and we'll work through these quickly. All right, so our calculator says, we add these two numbers together, our calculator says 10.24. So here's what we want to do. We want to look at which of these two numbers has the least decimal places. That's going to be this 7.0 because it's got a digit up to the tenths place. Again, I like to do this vertically. I'm going to leave that to you, how you decide to do it. This makes a lot more sense to me. I'm going to make that little line there. I've got a 4, a 2, and then a 10. 10.24. The 4 is not significant. It lies to the right-hand side of my line. Therefore, it's going to be, our answer will stay 10.2. And of course, this non-significant one is used for rounding purposes, but it is less than 5. So we leave the significant figures as they are. Next one, 100.0 grams minus 23.73 grams. Again, let's look at which of these two numbers has the least decimal places. It's going to be 100.0 up to the 10th place. Now I could round this, I could show this vertically again, but let's just see if we can do it without showing it vertically just to try it. Okay, so we know that our answer can only go up to the 10th place, all right? So it can only be these 3 digits, but we can use this for rounding purposes. It is greater than 5 or greater, therefore we round up. So our answer is 76.3 grams. All right, you try this one. We have 0.02 centimeters plus 2.371 centimeters. And our calculator says 2.391 centimeters. Go ahead on the sidebar and work this problem out and put your answer in. Okay, welcome back. We look at our two numbers in the problem. Which of these numbers has the least decimal places? Okay, now this one goes up to the 1000th place. This one goes up to the 100th place. It's got to be the one that goes to the 100th place because that has only 2 decimal places. Okay, so therefore our answer can only have 2 decimal places. And this is our first non-significant figure. It happens to be less than 5. So therefore we're not going to round up. We're going to leave those numbers as they are, and we will get an answer of 2.39 centimeters. Okay, I'm going to leave this one to you as well. Go ahead and work this problem out on the sidebar and let me know what you get. Okay, let's look at this one. This one's not too bad. We've got 2 numbers here. One has digits, it has decimals to the 10th place, and one has a decimal, has 3 decimals going to the 1000th place. Okay, the one with the least decimals is obviously the one that only goes to the 10th place. So therefore our answer can only go to the 10th place. Let's put a line there. And then we look at this one as our first non-significant figure. 2, of course, is less than 5. Therefore, we do not round up. We get an answer of 709.2 liters. All right, let's have you try one more and then we'll do the last one together. So look at this one, work it out on the side, let me know what you get. Let's look at this problem. We have this number, 1,818.2, only goes to the 10th place. 3.37 goes to the 100th place. The one with the least decimals is 1,818.2. So therefore our answer is limited to the 10th place. I'll put a little line here to help us out. And our first non-significant figure is greater than 5. Therefore we round up our last significant figure. Our answer is going to be 1,821.6 pounds. With this one, the problem's pretty simple since we have both of the numbers have digits to the 1000th place. So both have the same number of decimals. So that means our answer will have decimals to the 1000th place as well. Okay, there is a little trick here that is going to be important to understand. Okay, if both of your numbers go to the 1000th place, then our answer has to go to the 1000th place. And I'll show you what I mean there. Okay, look what our calculator says. Our calculator says 0.16 milliliters. All right, but in our problem, both of our numbers went to the 1000th place. All right, so we actually have to add a 0, 0.160 milliliters. We have to add this 0 to show that our answer is significant up to the 1000th place. Okay, so when our calculator did that calculation, it just dropped that 0. But in chemistry, we need to make sure that that 0 is included so that when somebody sees that number, they know that your measurements were precise enough to be significant up to the 1000th place. Let me erase that so that when the number comes up, it doesn't cover it.
All right, now you see the answer, and it says that that 0 had to be added. That concludes our discussion about significant figures. Hopefully they made some sense. If they didn't, come in, we'll talk about them. I promise you we'll figure it out. If you give us some time in tutorial, we'll get through it, we'll figure it out. But again, some practice and a little bit of thought around it, and these will come through. One of the keys to math is put in some time, put in some frustration, step away for a bit, go do something else, come back and look at it again. A lot of times those concepts will click while you're away. Have a great time. I'll see you at the next lecture.